Hi, I'm Alex, founder of Redwire Labs, and today I've got Abelino, principal engineer, with me, and we're answering some of the common questions that we get. So today's question is, can I create a low-power embedded system with nerves? And this isn't exactly a black and white answer, but there is a bit of a catch in this question, I think, and that's the phrase low power. So typically when you think about low power, you're tending to think in like low numbers of milliamps or microamps. So very, very low stuff that can run on, say, like a coin cell battery. And are you going to be running on a coin cell battery on nerves? And the answer to that is flat out no. That's really the job for other types of systems. However, if you rephrase this a little bit, you can turn this into more of a question around, can I run nerves on a battery powered system? And so then the question there becomes, well, how big of a battery? One answer there is, well, pick some large batteries. So there are some on the market, like lithium iron phosphate, for example. So this is not lithium ion. This is lithium iron, LiFePO4. And these batteries have a lot of capacity to them. So some of the ones that I have on screen here just make the math easy for 40 and 50 amp hour batteries. And now these are also 40 and 50 amp hours, for example, at 12 volts for these batteries. So if you're running a typical embedded system, you're down at 3.3 volts. Any of the ones with like a USB input have 5 volt input. So you've got to convert this more to watt hours than specifically looking at it in amp hours. Just to do some napkin math here, this isn't going to be incredibly precise, but we could say 12 volts times those 50 amp hours are going to give us around 600 watt hours here. And now we can start using that to figure out if we're running this into a system with 5 volts input, you'd have to use a voltage converter and you'd have losses and inefficiencies there and all that. But again, just theoretical napkin math. If we're running this more at like 5 volts, now we've got 120 amp hours to play with there. And if we take that down to like a number of days, so 24 hours, we could run that for 5 days straight for 1 amp hour. Something like a BeagleBone Black Texas Instruments AM335 processor. When we've hooked that up on the bench, that tends to run at around 250 milliamps. So say, well, let's just double that and say you've got some extra hardware attached to it for your, say, cape or peripherals or whatever else is hanging off of that. So we'll call it a 500 milliamp draw off of that, which will double the value that we've got here. So we can just multiply that by 2, and that gives us about a 10-day continuous runtime for a 50 amp hour battery that has a 12 volt output there. And that's also if you're running it just full blast too. So this also doesn't include any kind of sleep modes or energy efficiency settings, shutting down peripherals or stuff like that. So that can give you a little idea of if you're using a decently sized battery, yes, you could probably get this to run for a while. But in comparison, you're not going to have it running for like 5 years on a coin cell, for example. So another option that we've got is using a heterogeneous processor. These run a mix of ARM processors, different types of ARM processors. So you tend to have an A core and an M core, the A being the application core, which is a microprocessor, and the M core being a microcontroller.
On a traditional non-heterogeneous platform, such as the AM335, there are still other tricks that, the developers can implement in order to improve the consumption. And 2 of those that come to mind is CPU frequency scaling and also undervolting. For frequency scaling, there are a few strategies that the kernel itself understands and knows how to implement. And so you can give it a range of lows and highs, frequencies that to stay within bounds, basically.
So frequency scaling being a way to ramp up or ramp down the speed of the processor, higher speeds taking more power. So you can use those to execute your jobs quicker, But you don't want to idle at a higher frequency, for example, because then you're consuming power during that time, more power during that time.
Right.
So then when you're more in like an idle mode, or you're not trying to get tasks done, ramp down to the lower frequency so you're consuming lower power.
Yeah. And for undervolting, it's pretty much what it sounds like. You volt the processor at a much lower voltage, but that can have adverse effects also, and maybe long-term adverse effects on the actual hardware. But that pushes you into more modern heterogeneous hardware architectures, and where you have the ability to utilize a microprocessor and a microcontroller to accomplish low power. So in other words, these two types of processors need to collaborate by implementing suspend or resume methods to the system, so that it is cleanly powered down or brought up at a later point in time without data or service loss.
So the cool thing there being, with the A core and the M core talking to each other, or multiple A cores in some of these cases, because you can have dual core, quad core, octa core, whatever machines as well. That M core processor can work like a supervisor, like a low power supervisor, monitoring the entire system. And so it can spin up, it can boot the A cores when work needs to happen. So basically like booting your embedded Linux system at that point.
Exactly.
Your embedded Linux system then can go up and connect to the internet and pull down whatever it needs to, or push stuff out to a display, or data crunching, or whatever you're trying to do locally. Do that high powered work and then shut down, but not shut down your entire hardware, just shut down those power intensive application processors. And then your M core is still active, monitoring the system, but that M core itself also has low power and sleep mode. So it's not spinning in a high power state the whole time either. It's in a reduced sleep mode, but you still have some part of the system that's active that can wake up the rest of the system when it needs to do something.
On the AM62, TI did some interesting things on the microprocessor side of things, where they actually optimized the boot times. So as the MCU toggles the MPU between on and off modes, the boot time is much faster, and probably drawing about the same power. I don't know. I'm just making an assumption on that right now. But that was very interesting, because if you compare that to other strategies in a non-heterogeneous platform, for example, your Linux operating system on whatever machine, where the only true low power state is going to sleep or hibernation, it takes time to get out of those states, like a lot of time. And then there's the maybe other options, such as wake on LAN, for example. I've used that in the past for my machines. It works wonders, but still, like, the system has to come up, and that takes time. TI did a really good job with the AM62 MPU, where the boot up times between those stages is much lower.
And the TI AM62 being one of the processors that we do have a nerve system for, and that Redwire Labs does support. Probably the caveat there being, one of the things that is missing in the nerves community right now in general is that communication between A and M core processors. One of the common ways to do that is with RP message. It's communication bus that processors can use to talk to each other, either internally, like the heterogeneous processors have right now, or also externally to other chips on a board. So kind of a cool interface to be able to do that, but I haven't seen the nerve support for it yet. So just know that if this route sounds nice, there's going to be a little lift, or at least as at the time of recording this video, there's going to be a lift around that. With that method, that does also give you the interprocess communication facilities to do the wake and sleeping of processors in that as well. So that's pretty nice. Another way you could probably rig this up without that is through UART or something similar with those lines connected. So you're talking over a serial port at that point between parts of the system. It's just not as ideal though, since there's already another mechanism that's pretty well known to do it. But like I said, just not quite supported yet. So then that kind of leads us into the next option here, which is why not just go straight to a microcontroller? Because that's equivalent of an M-core processor, basically. Like, why even have the A cores there at all? And that's a good question. And I'd say if your application doesn't need that embedded Linux part of it, that A core part, then you probably could get away with doing the whole thing on a microcontroller. Microcontrollers these days do have the ability to connect to Wi-Fi, to Ethernet, to cellular. You have those Bluetooth. So you have that connectivity to other devices that's beyond just like a UART, beyond some serial port, beyond RS-232 or 485 or so on. So these microcontrollers are getting a lot higher powered these days in terms of what they can actually interface with. You're not stuck using an application processor, an MPU, to have to talk to Ethernet or through Ethernet, for example. So there's a handful of processors there that we like and that could also serve for these types of cases. Like the TI MSP430, for example, is designed to be an ultra low powered microcontroller. This thing is designed to sleep at microamps. So that can be one of those good tools for the job there. They also have the SimpleLink CC32 whatever so on series. There's a handful of part numbers in this series. But if you need to start working your way up into Wi-Fi, for example, actually I missed it on this slide, but like MSP432 gives you an Ethernet port. The SimpleLink CC series is when you start getting into Wi-Fi. So this board, for example, does actually have a Wi-Fi radio on it that's on screen here. And then if you need to go into cellular, which cellular is pretty high powered when it's active, then you're looking at something like the Nordic NRF 9160, for example, can give you cellular on a microcontroller. So Abelino, how do you integrate against this kind of stuff? And actually, I guess the caveat here is none of this is going to run Nerves at this point. So Nerves really needs an embedded Linux system, something that can run Linux to be able to run Nerves.
And our go-to tool to write firmware and run firmware on these various microcontrollers is Zephyr. Zephyr RTOS makes it really easy with their clean API and very good documentation to get started writing C-based firmware for these microcontrollers. And we also have various tools on GitHub to install Zephyr toolchains, to install the Zephyr-based RTOS using ASDF. We have a few plugins in our GitHubs just to make that much easier for entry, when it comes to entry for development. And if I remember correctly, when we were working on a project a few years ago around the NRF 52840, I do remember that on idle, on a very basic firmware, no optimizations, it was drawing around 0.5 milliwatts. So that's around 150 microamps. But I do know that, especially on their forums, people have claimed to have gotten down to 3 microamps, which is insane. However, their firmware was configured to be driven purely by interrupts, and I think that's key.
Yeah, so this is the types of systems that really start getting you into that territory where you can power these off of coin cells. These are what I'd call the truly low power embedded systems if you need to go that route. For the folks who have come to this looking for Nerves, for example, what's making it harder to put Nerves on a microcontroller? Like, why isn't it very feasible to do that?
The microcontroller is very specialized hardware with a fixed set of peripherals, whereas your Linux kernel is designed for general purpose microprocessors that have a very specific way to set up peripherals. And I think that's the biggest thing.
And so you mentioned Zephyr RTOS a little earlier. So that's the operating system, RTOS being real-time operating system. And that's obviously not Linux. So Linux has a certain API. If you're writing code against the Linux kernel, if you're in the kernel writing kernel drivers or stuff like that, you're following that driver API, the Linux kernel API, and really what Linux rolls up to is the POSIX API. POSIX being one of the open standards for how to interface code into POSIX compliant systems. So Linux, BSD,
anything Unixy.
yeah, anything Unixy. So an RTOS has a completely different interface under the hood. They might not be POSIX compatible. They probably aren't POSIX compatible, or the couple that I've seen that have like a POSIX emulator, like emulation layer, are typically around getting your network connectivity going. So being able to do something like LWIP, lightweight IP, to be able to get some kind of network connection established tends to be more along the lines of what that emulates, and not a full-blown 100% POSIX compatible API. There's a whole lot missing there from an RTOS that can't support nerves, really can't support the beam. The beam has OTP, Open Telecom Protocol, which is a giant framework and toolbox of some really great things that you can use, but also even has things in it like an FTP server, HTTP client, whole bunch of iNet stuff for internet connectivity, Ethernet connectivity, all that kind of stuff. It's got a lot of stuff in distribution, so like how you cluster nodes together. And you really don't even need all that stuff on a microcontroller, right? So the toolbox is nice when it's, available, but that toolbox is also big and comes with a cost. And when you're really trying to get to even more constrained embedded systems, where you're going down to that microcontroller level, when you're really trying to squeeze every bit of power out of that system you need to, having that extra stuff is just getting in the way at that point. And the flip side of that is the RTOS gives you a lot of those nice cities too, which is why we like Zephyr RTOS, for example, in that case. So some of the advantages that come along with the beam that Elixir developers really like with the beam tend to be its process management, its actor model, its message passing, its functional programming. It doesn't have an object-oriented programming model, so you're not worried about mutexes and locks and things like that. You have a completely different way of thinking about systems like that, and things that can really help you not have to spend so much on defensive design.
And also to mention memory management in your traditional Linux operating system, whereas in microcontroller land, you have to define your memory layout at build time.
Right. And so one of the reasons why we like tools like Zephyr RTOS is because it still brings a lot of that feeling that we like from Elixir into that microcontroller land. So we are programming in C at this point instead of Elixir, but we still have things like mailboxes and message queues and process management and tasks and ways to prioritize tasks and ways to do multi-threading and all that kind of stuff. But if you're using those tools right, an RTOS like that gives you a really nice system out of the box to help you avoid shooting yourself in the foot, like you might if you had to program all this on bare metal, for example, or, without those guardrails. It helps give you a path to better design patterns. So philosophically, Zephyr RTOS to us feels like close to those same types of concepts that we like from the beam, from OTP, from Elixir. But it gives us a way that compiles down to this even more constrained, even lower powered hardware. And those are the reasons why we look towards using one versus the other.
Zephyr also has a wide range of board support, which is a plus for us because we can switch to multiple different between hardwares during development, use the same code base, very similar to Nerves, how we can build a firmware for multiple targets using the same code base. We could do the same thing in Zephyr. It might be depending on the amount of peripherals on one hardware target versus the other, device trees might look different between those board targets in Zephyr, but Zephyr does, because of the concepts that they borrowed from Linux, such as device trees, they make it very easy to set that up for each target that you might be working on.
Absolutely. So yeah, just like in Elixir, how you have a mixed target that you can set, you can shift that between different devices, even the host computer if you want to run on that. And the corresponding Elixir config files, for example, that let you set up those different targets in different ways, depending on which one you're running on. In Zephyr, you have a similar type of thing. It's done basically through device tree. You can, kconfig really. And part of that is then you can pull in different device trees for different things. You can pull in different modules for different things. And it's a really configurable system. So same type of feel, same type of principles that you get from it. It just happens to be a different language. So this has been a little overview of being able to create low power embedded systems with nerves. Again, this is a question that we get a little bit, so great to finally be able to answer this, and we'll see you all in the next video. Thank you.